Hi everybody, welcome back to what might be for the last time, Chemistry 140. I say that because I looked at the number of slides we have left, and that plus the lab might finish today. So this could be the last lecture. But if it's not, we still have tomorrow. Administrivia things to talk about. Last call for quiz number 8. Quiz number 8 was due yesterday. It's still open for one more day, like all the rest of the stuff. So that's due tonight. Make sure that you get that in by the deadline if you have not done so already. Lab worksheet number 4 is due tomorrow. There is a one-day extension on that too. And if we do finish everything today, then at the very end of the lecture, I will talk about what's going to happen for the rest of the week. Okay. I don't know if we'll actually get through all of the content. There are a lot of practice problems in these sections, but there are only, how many more slides again? Yeah, I only have 21 slides, so that plus talking about the lab, we could probably get that done in 2 hours, so let's get started. So, the other day we talked about how you could have solutions be concentrated or dilute. And we attributed the difference between the two to just the color. So, like, if a solution was blue when the solute was dissolved into it, if it was less blue, we'd call it dilute, and if it was more blue, you'd call it concentrated. But visual appearance of a solution is not a really great rubric. We need something that will give us quantitative information about it, particularly if the solution is clear and colorless, right? If I put salt into water, it doesn't change the color, so I can't tell if it's concentrated or dilute without doing something like tasting it, and that's obviously not a good strategy for other chemicals. Now, appearance-wise, again, this is what that would look like. So a concentrated solution would have a lot of particles of solute. These little circles right here, these are the solute. And the more of them I have per unit volume, the more concentrated the solution is. So I'm going to box in my unit volume. I can do the same thing over here. There are far fewer particles of solute in that unit volume. Therefore, that solution is more dilute. The stuff in the interstitial spaces between all of the molecules is presumed to be water. Now, if I want to take a concentrated solution and add water to it, I can make a dilute solution, because if I added water to this solution here, then all of these molecules would then spread out, right? I would fill in the space with them with more filler. And so I would dilute the solution that way. And if I were to look at the dilute solution, there would be fewer particles in that same size of a square. There. So that's what we're going to do. We're going to learn how to concentrate solutions and dilute them. And principally, dilution is a really common technique. You just take a known solution and then add water to it. Now, numerically, the formula we're going to be using for concentration is this. It's called molarity. And the calculation is actually pretty straightforward, but the application of this is going to be extremely useful. So the formula for molarity is just how many moles of solute do you have divided by liters of solution. Notice that the word solution is used and not another word like solvent. What that means is that if I am preparing a solution, let's say I have like table salt or whatever. This is some volume, but I don't really care about the volume of the solid because I usually just determine masses of solid, right? And I put it in a container with this much water, maybe 1 liter. If I put this in here, the volume is going to increase very slightly. and then this won't be a liter anymore, right? So measuring the volume of the solvent doesn't really help us if later on we're going to measure how much solution we have. So we define molarity from the perspective of the solution. The volume of the solution should be everything put together. So mix your two things together and then determine the volume of the solution. They don't have to be mixed homogeneously. They just have to be mixed enough so that it's all dissolved in there and you have your solid dissolved into the solution. And it's not just like outside of the solution stuck to the container wall or whatever. So let's do an example. If I have 2.00 moles of calcium chloride, I would just write that divided by this volume, 1.75 liters. You just punch the numbers, just as shown. And so the number I get here is 1.14 moles per liter of calcium chloride. Now, that gets cumbersome to write all of those units out every time, but you'll notice that here my units did not cancel because moles doesn't cancel with liters. So instead of canceling things out, I just write both of them, and then I condense them down to this, capital M. Whenever you see capital M used, that indicates molarity, or moles per liter. Be very careful about that because capital M is also the unit for mega, so 10 to the 6, and capital M in molarity that is very different than the mega unit. Now, obviously, we don't work with moles in terms of like physical go to the balance and weigh out a number of moles thing, right? Like, that's not a quantity that is typically measured out physically. We measure in mass instead, so it's much easier to weigh out 10 grams than it is to weigh out 1.5 moles. You have to do a calculation. So what you're going to have to do most of the time is you're going to turn grams into moles and then divide by the volume of the solution that you're using. Now, when we're in the laboratory, we're going to need to make solutions. We use solutions because the liquid phase is just so much easier to work with than the solid phase. We can observe chemistry happening in the aqueous layers of a solution much easier than if I had two solids and I sat them on top of each other. So it behooves us to know how to make a solution in the laboratory. And it turns out that to make any solution with a solid reagent and water follows the exact same process. So here's what you would do. Let's suppose that I wanted to make some concentration and some volume. What I'd need to do is I would need to figure out the amount of solid to put into the container. And the way that we do that is the following. Let me zoom this in. So I have a screen that doesn't write. That's great. There we go. So I have my solid sodium chloride. It's on my little weighing boat here. And I have a flask. These are called volumetric flasks because on the flask is a line. And when you fill the flask to that line, you have measured out that volume. So this is called a volumetric flask. This is different from the Erlenmeyer flask, which looks like that. That actually looks exactly the same as what I just drew, so. You type in volumetric flask in Google, and you'll find a picture of it. It just, the bottom is rounder and the top is narrower, whereas an Erlenmeyer flask looks kind of like, I guess I could draw it like this. It'd be more triangular. So what I need to do is I need to put some quantity in here, but how much do I put in here? Well, if I want a 1 mole per liter solution, and I want 1 liter of it, that would mean that when I multiply those two things together, the units would cancel out, and I would be left with 1.0 moles of solid that need to go in here. Now, what is that solid? It's NaCl, so let's indicate that. And then what we'll do is we'll turn it from moles to grams. Now I need to know the molar mass of sodium chloride, which I have to go to Lentech to find, so let's do that real quick. Lentech. And I think it's 58.44, but I just want to check. Formula did not parse correctly. Oh, I double typed the L in NaCl. Great, that's going to be there forever. 58.44. And that times 1 is just 58, because I only have 2 sig figs. So now that I know the amount of solid to put in here, that would be the amount that would be required for a 1 molar solution, or 1.0 molar solution. But we have to be considerate of the definition. Remember that the definition of molarity is moles of solute over liters of solution. So we need to consider the order in which we do these steps. So here is how we're going to make our solution. Once we've done the calculation, we're going to do this for our solution. Step 1, we're going to add the mass of NaCl, which in this case is 58 grams, to the flask, which is 1.0 liters in this case. So we're going to put the salt in first. Then we're going to add water. How much water are we going to add? We're going to add enough water until we hit this line. I'm not going to measure out an amount of water. I am just going to add water until I hit the line. Because whatever volume of salt is in there, I'm going to add water and swirl it around, dissolve the salt, and then I'll keep adding water until I hit that line, which would be 0.999998274, whatever liters, right? But who cares? There's a line on the flask that tells me when I get to 1 liter. So just add enough water until you hit that. And then once you've done that, you want to mix the solution until it's homogeneous. Mix it really well. There is one secret 4th step. Enjoy. I had students who started writing enjoy at the end of their steps, and I don't know why that helped them memorize it, but I liked it, so I now include enjoy for you to enjoy. Or maybe they were just alcoholics. I don't know. I teach all ages of students. I realize most of you in 140 are probably Orca, or high school students, or of the like. So you don't get to enjoy any ethanol solutions, we'll say, just yet, but someday. All right, there's our picture of what's going on here. Now you can see here that I've got my salt in the container. And I am putting the salt into the flask right here. Now, in the water step, the proper way to do this is to not just add the water to here, but also to add it into this thing. And rinse out all of the salt that might have accumulated on the sides here and didn't fall out. Then we would rinse the sides of the funnel until it all gets washed into there. We want to ensure that we get every last bit of that 58 grams that we added there into the container. So good technique will ensure that you have an accurately prepared solution. And that technique, it requires you to just basically, anything that the salt touched, rinse it off 1 or 2 times to ensure that you got all that salt and it made it into the solution. Then you want to add the water until you reach the 1 liter mark. Now, your fill line is going to look something like this. If you're adding water and you stop at this point, you have too much, or you need to add more water because you haven't reached the line. This is the correct fill. I'm trying to make it touch the line like that. You know, I can do better than that. Let's try that again. There we go. Your meniscus, that's what this curved line is called, this is the meniscus. The meniscus should touch the top of the line. If you do that, you will have 1 liter. That is how the solution has been calibrated. Now, what happens if you go too high and you go like this? If you overfill the solution, you can't just remove that water, because the second the water gets into the solution, it mixes with any salt that's in there. So removing the water would also remove the salt. And when you change the volume, its concentration would still be whatever it was when you diluted it extra. If you overfill your solution, the solution is wasted. You've diluted it too far and you can't get it back unless you have a way of only removing the water. Typically speaking, the way that we remove water from stuff and not the solute is to boil it. But you're not going to sit there and boil away 1 milliliter of water, which would require you to heat up the entire thing. That's ridiculous. So, if you really care about the concentration accuracy, you dump out the solution and you just rinse everything out and you prepare it again. So, there is a degree of carefulness that you have to employ here. If you go over the line, you gotta do it again, and that's no good. Once you have filled your solution, though, and you've put the cap on it, you're safe, as long as you don't accidentally spill everything everywhere before you use it. Super loud airplane going over. But you do want to mix the solution. If you don't mix it, then down here, this part of the solution will be more concentrated than this part up here will be. And when you go and use it, you won't have equal concentrations for the portions that you're allocating. So be mindful of that. Make sure that you are mixing the solution well before you use it. Statistically speaking, the way to properly mix is to invert 50 times. What that means is if you hold the solution in front of you, spin it upside down so your thumb is over the lid, holding it in place, let the water drain so the air bubble goes to the top, and then flip it back right side up. That would be 1 inversion. You can do that in like 1 second. So basically invert it for about a minute, and you'll get a homogeneous solution. So what I want you to do is I want you to apply this strategy, all, I think, 2 of you that are watching right now. I want you to apply this strategy in preparing a solution. I'm going to give you KBR, and I want you to make this molarity of solution, and I still want 1 liter. So first find the mass of KBR you got to add. So to do that, you'll need to find the number of moles, multiply the molarity and the volume together to get moles. Once you know the mass of KBR that you're going to put in the solution, describe using 3 steps how to make that solution. Type your procedure into the chat, going with step 1, step 2, step 3, just like I did before, okay? We'll go over the answer to this problem in just a second, once I figure out why my cats are yelling at me. One more minute, we'll go over the answers here. All right. Here's how we prepare the solution. So, if I have a 3.50 mole per liter solution times my volume, I would get moles. Moles of what? Well, we're working with kBr, so let's append that. And then we will convert moles of kBr to grams of kBr. And we'll look up the molar mass of this. I forget what it is. It's pretty big, though. Oops. kBr. 119. When I multiply these together, I want to say this is 417. But, yeah, 417. Some problems you just remember the answer to. Okay, so that's the mass that I need for the solution. So what I'm going to do is I'm going to weigh out in my weighing boat 417 grams of kBr. We're going to put it in the flask. Specifically a volumetric flask, which has a volume of 1 liter. Then step 2, we'll add H2O to the fill line. There's my fill line. And then step 3, mix really well, 50 times or more. And of course, enjoy. All right, there you go. That's how you make a solution. All right, so we did all those things. Any questions, let me know. So like we saw on the previous slide there, molarity relates moles and volume in such a way that if you multiply molarity times volume, you get moles. So if I write out the formula, molarity equals moles over liters, which I'm going to write as a volume, I could multiply both sides by V to get molarity times volume equals moles. There's the formula. It's just another use of the molarity formula. Now, something to note is that we need to use the volume in liters because molarity is defined as number of moles of solute per liter of solution. So if I give you a problem like this, where we have a volume of solution, but it is in milliliters, you'd need to do a conversion. I clicked the wrong thing. There we go. So let's figure out how to calculate how many moles are in that solution here. So if I have 0.350 moles per liter, which I'm going to then erase, and I'm going to write it like this. That's the same thing, right? Writing our units like that is going to help us when we get to stoichiometry in just a little bit. Oh man, I keep sneezing here. Sorry if I just mute for like a 10-second awkward pause. It's me sneezing. All right, and then I'm going to multiply that by the volume of the solution. And obviously those units aren't going to cancel out. So what I need to do is I just need to turn this from milliliters to liters so that these will cancel out. And then whatever the result of this is, that would cancel out too. But obviously, since I'm just multiplying these things together, I don't need these parentheses. So in 1 milliliter, there are 10 to the minus 3 liters. And now I just run the numbers through my calculator. I could if I could turn my calculator on. There we go. Oh, I hit the wrong button too. There we go. And then what are these moles of? They are moles of magnesium hydroxide. Which, if it helps you, you could be writing that all along too. That's not strictly necessary for these types of problems. Later on, we're going to get to problems where it will be very important that we add the moles in at some point. And then if I wanted a mass of that, I could just turn moles of magnesium hydroxide to a mass by looking up the molar mass or calculating it from a periodic table. So no problem there. All right. Now, since we have gotten to this point where we can figure out masses from moles and we can calculate moles using molarity and volume, we can now ask all sorts of crazy questions. So I'll give you about 5 or 6 minutes to try these two problems. Or 4 problems, I guess. So the first one asks how many moles of HCl are in this sample? And then how many grams is that sample of HCl? And then down here, the second problem, if you have 250 milliliters of 3 molar potassium dichromate, you could find the mass of potassium dichromate once you know the number of moles, and then you can find the mass of just the chromium atoms in the solution. How the heck do you do that last one? Think about chapter 13 and 14 when we were trying to do mole-to-mole ratios within a formula. How many moles of chromium are in a mole of K2Cr2O7? That'll help you. So I'll give you a few minutes to do that, and we'll go over the answers together at the end. See you in a bit. 1 or 2 more minutes and we'll go over the answers. All right, let's go over the answers here. Let's do the first problem first here. All right. So if we're looking at a beaker with 35 milliliters of 2.50 molar HCl, first we want to find the number of moles of HCl in there by multiplying these two terms together. So 2.50 moles per liter times 35 milliliters, but that should be in liters, right? So there's milliliters, which will then cancel out and do the conversion to liters. So that now these units cancel out. I'm left with moles, and in this case, these are moles of HCl. And I get 0.0875 moles of HCl. There you go. That's the first answer. And then I want to turn this into grams of HCl. So we'll turn moles of HCl into grams of HCl. And I got to go to Lentech to find that. HCl 36.46 grams per mole. So the number of grams of HCl that must be in this container must be 3.190. So 3.19 grams HCl. All right, so that's the first problem. Let's do the second problem here. I'll just scroll that up there. So I need to know the mass of K2CR2O7. I'm going to do this the same way. So 3.00 moles per liter times, how many liters do we have? 250 milliliters. So 250.0 milliliters. And I got to cancel those units out so that they're in the correct unit. So 1 milliliter, 10 to the minus 3 liters. So that's going to give me the total number of moles of K2CR2O7. And so that is 0.750 moles. Now I'm going to need this number for the second calculation, so I'm going to just hang on to it. We're going to go down to calculate the next part. So first problem we want to figure out is the mass. So if I take this number and I multiply by the molar mass, so turn the number of moles into grams. Got to go to Lentech for that too. Oops. Oh, what did I just do? There we go. For some reason, Alt-tabbing made it full screen. So K2CR2O7. So I got 294.18, I think it was. Let's see here. Yeah. Oh, for some reason, all of my commands disappeared because Photoshop is being obnoxious. That's okay. I'll deal with that later. So this will give me the mass of K2CR2O7 in there. And so that is 220.6, so 221 grams of potassium dichromate. That's how much is in the solution. Now, what's the mass of just the chromium? Well, I still have this much potassium dichromate in terms of moles. But I also know that for every 1 mole of potassium dichromate, I have 2 moles of chromium, right? Because this 2 right there tells us that. So by doing this dimensional analysis, now I have moles of chromium, and I can just go moles of chromium, grams of chromium. And according to the periodic table, 1 mole of chromium weighs 51.996. That should be a decimal point there. Grams. And so, after I cancel those units out, punch in the calculator, I get 78.0 grams of chromium. There you go. That's how you solve those 2 problems. Or 4 problems, I guess we could say. All right, give me a second. I'm going to reopen Photoshop because I hit a button. I made it angry. There we go. All right, let's go to the next problems. So these are just more problems for you to practice with for using m times v equals moles. I'm going to leave this example for you to practice because the answer is there. But I am going to do these problems for you here. So we'll do these together. You can pause the video if you want to try these on your own. But because we're coming up on the break, I want to just do these problems and then we'll take our break. Sorry, I was confused, like what I was looking at there. There was like a different button on Photoshop now. Like, I don't know what's going on. I just want to write on the tablet. All right, so we have 1.50 moles per liter of CaBr2. And I want to know the mass of CaBr2 in 100 milliliters of this. And so I need first turn this from milliliters to liters, so that those cancel out. And 1 milliliter is 10 to the minus 3 liters. So that would be the number of moles, and these are moles of calcium bromide. And that should be 0.150. I want to then find the mass of that. So we'll go moles calcium bromide to grams calcium bromide. And we'll go to LenTech. Now, if it helps you figure these problems out, writing out a little blueprint or flowchart, by all means, please do that. So this is 1 mole is 199.89. Is that right? Yeah. Yeah. There you go. So I get 30.0. That should be 0.150, yeah. There you go. That's a little more clear. Now for the second problem, we have to work backwards. We need to figure out what volume is needed to obtain 5.75 grams of calcium bromide. So we're going to do this problem backwards. We're going to start with a mass instead, then turn that into moles, and then use molarity to tell us the volume. So let's do that. So if I start with 5.75 grams, I can turn that into moles. And so 1 mole is still 199.89 grams. So there's my moles. But if I want to go directly to molarity, I could just do this. Moles of calcium bromide per liter, right? And then these would cancel out, and this would give me a volume. What's the relationship between liters and moles? Well, for every 1 liter, I have 1.50 moles of calcium bromide, because that's molarity. I've just put the relationship upside down, haven't I? But it's the same relationship, right? This is the number of moles per liter. So hitting enter here would give me a volume. And I got 0.1917 liters. So 0.0192. And you could turn that into milliliters pretty easily. But the problem does just say, hey, here's a volume, or hey, solve for a volume. You can tell me whatever volume units you want. Just don't do something like barrels or hogshead or something silly like that. All right, and then for the last problem, we're going to do the same thing. I have 35.9 grams of KBr. What's the maximum volume of 0.8 molar solution I can make out of that? So we'll just follow the same process. We'll start with grams. We'll turn grams of KBr into moles of KBr. And I gotta go look up that number. Hold on. Is it 119? Yeah, 119. Oops, that's the wrong screen. Hold on. There we go. 119 grams per mole. And then if I divide by the molarity here, so moles of KBr per liter, that'll give me a volume that I can make. And I want my molarity to be 0.800 moles per liter. So that would be the most volume I could make out of this. Which would be 0.377 liters, or 377 milliliters. So if I needed a 0.8 molar solution, I could make, at most, 377 milliliters if I used all of it. All right, so those are some calculations that we can do using molarity. When we get back from the break, we will talk about dilutions with liquid reagents instead of solid ones, and we'll do some last calculations using molarity in a process called titrations. And those steps are going to be useful for talking about the lab, which it sounds like from the pace of the things, we'll talk about the lab some more tomorrow. All right, so let's put the break card up here. We'll get the music going and the timer going too, of course. And I'll see you in about 10 minutes.
now, face reality, never be charity. The enemy you're fighting covers all society. Damn right, bum's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, this destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then I'm a rival. Round up around, spit out, all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, they this too loud. This was this sound, and bombs whole ground. So round up, don't ease your pace, cause enemies brutal. Home of the truth, there ain't no truth. You're the only one war, one law. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby.
Here's a wake, anger breathes out, face reality, never be charity. The enemy you're fighting covers all society. Damn right, bum's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, this destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then I'm a rival. Round up around, spit out, all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, they this too loud. This was this sound, and bombs whole ground. So round up, don't ease your pace, cause enemies brutal. Home of the truth, there ain't no truth. You're the only one war, one law. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down.
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey yo. Here's a wake, anger breathes out, face reality, never be charity. The enemy you're fighting covers all society. Damn right, bum's not here, gonna fight all night. Right here, shadow 10 o'clock direction. Seize the moment, this destroy the nation. You rhyme slow motion, give me motivation. Breathe out now.
Hi everybody, we are back. Alright, what are we doing now? We're diluting stuff. That's what we're doing. So, let's take liquid solutions that have already been prepared and change their concentration to whatever it is that we want to, as long as that concentration is smaller. That action is called a dilution. You add water to a concentrated solution to reduce its molarity. Now, there is a special formula that we use for dilution, and that is this right here. It's called the dilution formula. And the reason that it's called the dilution formula is because it only works for dilutions. And I'm writing that in capital letters because for whatever reason, everybody loves to apply the dilution formula to everything they can think of with molarity. But this only works if you're doing a dilution. If you're doing a titration, if you're doing a reaction, if you're doing a conversion, doesn't work. Don't use it. It seems to work. You could plug the numbers in, but you just get the wrong answer. Okay? So, again, only works for dilutions. Now, each of these sides of the equation is just molarity times volume, which means that when I multiply it together, I get moles. What S stands for is the stock side, or the starting side. That's the solution you started with. And D is the dilute side. What that means is that when I do the dilution, the only thing I'm adding is water. So the number of moles of solute remains the same in both cases, before and after. I just need to find out how many moles that is when I do the calculation. Will dilute be a key word? I wouldn't say the word dilute, but in the context of the problem, I would tell you we need to make a different solution, and that solution will have a smaller molarity. So I might not use the word dilute, but the context of the problem should imply, oh, you are doing a dilution. So let's see what each of these parts stands for. So M is the concentration of the solution that is being used. MS is the stock solution. MD is the dilute solution. Let's add some notes here. So the stock solution will be written on whatever bottle you are pulling the solution from, and it will also be the bigger concentration. Because if you're doing a dilution, the stock solution has to be the larger concentration. Otherwise, it would be the dilute solution, right? So if you're looking at a problem and you don't know, excuse me, which solution is the stock concentration, it's the bigger number molarity, by definition. MD is the concentration of the dilute solution, and you get to choose this. If you're preparing the solution, you get to choose, as the preparer, what the dilute concentration is. If you want it to be more dilute, add more water. If you want it to be less dilute, add less water. The V's are the volumes that you need. So VS, typically, this is going to be what you calculate. But the V for the dilute solution is chosen by you. So, generally speaking, the D side of the equation, you get to pick. I want this molarity, and I want this much of it. And then since the molarity on the stock bottle is written there, you calculate the last thing, which is how much of the stock bottle should you use. Because some volume from the stock bottle will give you a number of moles, and that number of moles should be your dilute concentration times the volume you want. If you want a bigger volume, you need more moles to fill that bigger volume. So in almost all cases, we're going to be solving for V sub S. Not every time, but if you're doing a dilution, that's the number you're going to calculate. So let's do an example. I want to find 10 molar calcium chloride in my stockroom, and then use that bottle to make 3 liters of 0.5 molar calcium chloride. Well, I find a bottle, and it says 10 moles per liter on it. Somebody made this in the past so that I could use parts of it to make these solutions later. So what do I do with this? Well, let's do the calculation. And then we're going to dilute the solution, just like we did with the solid example when we prepare it. I gotta zoom this in because having so little space is driving me crazy. All right, so we're going to use the dilution formula. Oh, sorry, this is S and D for this class. So you could label them 1 and 2 for before and after. It doesn't matter. So when I'm preparing my solutions, this is what I do. That's not what I do at all. Hold on. I was trying to make that. This is what I do. I'm sorry, I was confused. I make a little grid. So this will be MS, this will be MD, this will be VS, and this will be VD. So now what I'm going to do is I'm going to go look through the numbers and just plop them in the grid so that I can organize my information. So I have 10 molar calcium chloride from the stock room. So that's clearly the stock concentration, MS. I want to make 3 liters of 0.500 molar calcium chloride. So this must be the dilute concentration, and this is the volume of it that I want. What that means is that I'm going to solve for this because that's the amount that I need. Because if I multiply these two things together, I should get moles of solute. And if I multiply these two things together, I should still get that same number of moles of solute. So I'm going to rearrange my equation such that it solves for the volume of the stock solution. And then I'm just going to plug in the numbers. So the molarity of the dilute solution was 0.5 moles per liter times the volume of the dilute solution, which was 3 liters. That should be a decimal point. There we go. And then I'll divide by the molarity of the concentrated solution. And what you'll notice is that all the units cancel out except for the volume, which is what we're solving for anyway, right? If we're solving for a volume, I should end up in liters. And what I get is this volume. So what that's telling me is that if I had 150 milliliters here, or 0.150 milliliter, or 0.150 liters of 10 molar stock solution, I would have the same number of moles in that concentration and volume as I would if I had 3 liters of 0.5 molar solution. The only difference between the two would be water. Now I have to do the prep. So I have my container that has the stock solution that I've measured out. So this would be my 0.150 liters of stock solution. That's going to go into my volumetric flask. And then the remainder will be H2O. So let's write out our steps just like we did before. So step number 1, measure stock solution. And the amount that we measured was 0.150 liters of 10 molar calcium chloride into the volumetric flask. And the volumetric flask had a volume of, 3 liters. We want to be specific because if I'm writing these directions down, I want the directions to be useful in the sense that I could apply this template to anything I want to. I'm just replacing what goes in the parentheses each time, right? But at the same time, I wanted to be specific enough so that if I gave this to somebody who I didn't know and who hadn't taken this class, they could look at this and go, oh, okay, I know exactly what to do, right? So if you're writing a procedure, you want to get the directions just right so that there's no discrepancy and no ambiguity. Nothing ambiguous about your directions. All right, step 2 is you're going to add H2O until you hit the mark on the flask. And then step 3, mix really well, 50 times or more. And of course, step 4, enjoy. All right, that's how you prepare a liquid solution. Here is the pictorial version of that from a textbook that I used to teach from. And again, what we would do to ensure good technique to get everything out is that we would rinse all in here, make sure that you get all the sides, rinse down the sides of the flask and the beaker, and swirl it to make sure that it all gets in there. All right. Now that I've diluted a solution for you, I want you to try it. So a common concentration that we sell HCl as, not we, I mean we buy HCl as, 14 moles per liter. This is about as concentrated as you could make it. So that's way too concentrated. That will start dissolving metal very quickly. I want to make 1 molar HCl for a lab experiment, and I want 1 liter of it. Tell me how to make the solution, and what volume I need to dilute, and what all the steps are in order. Okay, I'll give you about 3 or 4 minutes to do that, do the calculation, and then write out the steps, and we'll go over the answer in just a second. All right, one more minute. We'll go over the answer. All right, so let's compute the solution here. Ah. All right, so the stock solution is 14 molar HCl, so we'll write that down. I want to make 1 molar HCl, and I want 1 liter of it. So I need to figure out how many moles I'm going to take out of the bottle for that, which means that I'm going to solve again for Vs. Again, you're going to be solving for Vs most of the time. Now you'll notice that I'm writing capital M instead of moles per liter, just to simplify. Because they're going to cancel it anyway, right? So there's the volume of stock solution that's needed to turn my 14 molar solution into a 1 molar solution with water. And so we would prepare that by adding the stock solution. And then write what it is, 71.4 milliliters of 14 molar HCl to the volumetric flask. And that flask has a volume of 1 liter. We're going to add H2O to the mark. And then we're going to mix well. And then we're going to enjoy. Please don't enjoy your HCl, though. Like, don't drink that. That's bad. All right, so I have 2 more molarity problems for you to try. I think we'll stop after this point because we'll do the last stoichiometry problems tomorrow with the lab. I don't want to have like a 10-minute class tomorrow because I couldn't finish everything, so I don't want to rush through the next problems in 20 minutes. So I'll have you do these problems. One of these problems, in fact, it's this first one up here, you're going to be solving for something different than VS. So be careful. Do the little grid read the problem and figure out what exactly you're going to solve for. And then the bottom problem is just like the other problems we've done. So remember, make that grid. That grid will help you organize your information. Okay. Solve these 2 problems. We'll go over the answers in about 5 minutes. 1 or 2 more minutes, we'll go over the answers then. All right, let's go over the answers here. We'll go back to, oops, that's the wrong screen. So this first problem requires us to solve for a different component. But let's just set up our grid here. So the molarity part is pretty easy to put down the right numbers here. So I start with a 15 molar solution, and I end with a 3 molar solution. Now the question is asking, to what volume would you dilute 0.2 liters of a 15 molar solution? So the 0.2 liters must be this. So we're going to solve for the dilute volume. In other words, what the question is asking is, what will the final volume be of your solution if this is what you're starting with and this is what you want as your molarity at the end? So we'll do algebra. We'll just rearrange the equation. And then we'll plug in our numbers. So there's the molarity of the stock solution and the volume of the stock solution divided by the molarity of the dilute solution. That should be a dot. I did that in my head. I hope that that's right. 15 over 3 is 5. Times 2 is 1. Yeah. There you go. So if you want to dilute a 15 molar solution to a 3 molar solution, and you're starting with 0.2 liters, the final volume will be 1 liter. Now, the question did not ask us for a procedure, so we don't need to print that. We just need to answer the question. And the second one doesn't ask us for a procedure either, so we'll just answer the question as written. So, same as before. Make a grid. What volume of 6 molar sodium nitrate should you use to prepare 0.525 liters of a 1.2 molar sodium nitrate solution? So this is the concentrated side. This is the dilute side. And I want 0.525 liters of the dilute. So I'm going to solve for that. We'll solve for Vs. And that would be 1.20 moles per liter times the volume that we want divided by the molarity of the stock solution. And I don't have the slightest idea what number this will be. .105. There you go. That's the volume of that solution. I would need 0.105 liters of stock solution in order to dilute that stock solution to 525 milliliters and have a concentration of 1.20 molar. All right, those are the questions for the dilution section. So when we come back tomorrow, we're going to do the stoichiometry section, which is basically just, oh, it's unit 13 or unit 14 again. 14, 15, I forget. Whichever one we did stoichiometry in. We're going to use balanced chemical equations and use molarity to do, oh, I have this many moles, so I can calculate the number of moles of this other thing and then grams of that. So it's just an extension of that, and it's the last thing that we need to know in order to talk about the lab. So we'll do the lab worksheet discussion tomorrow. But for today, that is all that we have. So I will see you for tomorrow's lecture, which will be the last lecture. And we'll go over the last of Unit 16 then. So have a good evening, and we'll see you tomorrow for the end of the class. Take care.